So we can regroup this a little bit. Be careful to notice when they're repeated. So let's see here. I've got an x plus 1 on its lonesome. Oh, not on its lonesome. X plus 1 what? X plus 1, how many of those? Yeah, cubed. And then x minus 1 squared. And then a lonesome x plus 2. So it's a quartic times a quadratic in the initial denominator. It's a 6th order polynomial. And the resulting factorization has 6 things. That indicates to me I haven't missed anything. All right? Now once I have that, I can write down the partial fractions decomposition. That's a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed plus d over x minus 1 plus e over x minus 1 squared plus f over x plus 2. And that would be the answer to this problem. You know, if I have a problem like this and I say do not determine the constants, just set it up, am I impressed when you go and take 30 minutes to find the constants? I am not impressed. Because then at the end of the test you write, I didn't have time. Yes, because you did not follow instructions. I do not mean for you to actually find the constants on that problem. Because finding the constants on that problem would take an inordinate amount of time. Don't do it. Yep. Yes. You need to understand how to set up the partial fractions decomposition for arbitrary rational functions. That is true. Which is why I'm continuing to give you more examples. So another one would be like 3x plus 2 over x squared plus 4x plus 5 times, let's say, x cubed plus 4x squared plus 5x. Here's another one. All right. So this one, again, every time you need to come to terms with what the denominator looks like. So we've got here x squared plus 4x plus 5 squared times x. This we haven't seen yet. I haven't told you what the partial fractions decomposition looks like when we have an irreducible quadratic squared. Right? Here x squared plus 4x plus 5 is irreducible. It's squared. What's the partial fractions decomposition? I mean, this right here is a rare Pokemon, but let's take care of the 1 over x. That's simple. That just gives us an a over x term. When this is squared, what you do is b times x plus 2 plus c over x plus 2 squared plus 1. I mean, anyway. And then plus d times x plus 2 plus e over x plus 2 squared plus 1, and then the whole thing squared. So it's reminiscent of what we did in the repeated linear case, but we just square the denominator. That ends up being the partial fractions in this case. I'll stop. This will be my last quick setup, and then we'll go back to one with numbers. So here I have, this one's nicer, right? There's no factoring. I already factored it for you, right? So this is a over x minus 1 plus b over x minus 2 plus c over x minus 2 squared plus dx plus e over x squared plus 1. But this is an irreducible quadratic squared, so I also have an fx plus g over x squared plus 1 squared. It's a little bit nicer than the previous example because it didn't have that completing the square noise, if you will. So you see we're kind of merging what we did with the linear versus what we did with the quadratic, irreducible quadratic, when they're both present at once in the denominator. There are some very general guidelines that are kind of easy to see, to check yourself and whether you're right. All right? Can you tell me what the relation is between the number of undetermined constants, a, b, c, d, so forth, and the degree of the denominator, rather? Yeah, they're the same, right? Denominator here was quartic. I have a, b, c, d, 4. Denominator here was 6th order. I have a, b, c, d, e, f. That's 6 letters. Denominator here was 5th order. We go a, b, c, d, e. Denominator here was what? 1, 3, 7. I get all the way to G. And there should be no duplication in the list, right? See, here's the thing. You might be like, why don't you just do, instead of this, why don't you just do b over x minus 2 plus c over x minus 2? Wouldn't that be what you should do? No, it would not, because this is just b plus c over x minus 2. And this is just an arbitrary constant, so if you don't distinguish the denominators, you're not putting down a different thing here. In some sense, it doesn't count. All right. Now, I'm not going to prove that that's all there is, but it is all there is. And you don't want me to prove it anyway, because that is a problem of abstract algebra, which is not what this course is. All right, so an example, a rather beastly example. Eight x to the 4th plus 16 x cubed plus 76 x squared plus 45x plus 150 divided by x to the 4th plus 5x squared. All right? Integrate. So what would the first thing we needed to do, what would the order of attack be here? Notice it's fourth order, right? So first order of business is to do the long division. So let's do that. So we've got ourselves an 8x to the 4th plus 16x cubed plus 76x squared plus 45x plus 150. X to the 4th plus 5x squared is my dividing polynomial. How do I get this from that? 8, yeah. Multiply by 8, I've got 8x to the 4th. And here's a bit of advice. 8 times 5x squared. Where should I write that? Yeah, write it over here so that you don't accidentally subtract the wrong things, right? So we subtract and we get 16x cubed plus 71x squared. Oh, thank you. I was like, I don't remember a 71 in my in-between work, and there's a good reason for that. Thank you. So that actually is 36x squared, 45x. And that is the remainder. So what we just learned is that this is equal to 8 plus 16x cubed plus 36x squared plus 45x plus 150 divided by, and let me just say, what is this? It's really x squared times what? x squared plus 5, right? So what kind of decomposition can we do here? So let me call this thing g of x for just to give it a label. G of x can be rewritten as a over x, right, plus b over x squared plus cx plus d over x squared plus 5. So what you do, yep.
How do you know what the numerators are supposed to be like? How do you know if it's just an A or B or if it's a CX?
That's the partial fractions decomposition. That's what we're learning. It's complicated. It depends on whether or not they're repeated linear or if it's irreducible quadratic. Yep.
Determining what's underneath A, B, C, and D, is that just for memorization?
Yes.
Or are you, okay.
Yes. I mean, there's a pattern to be seen here, which I'm trying to share with you in examples 5, 6, 7, 8. But again, the general algorithm is to, first of all, write it as a proper rational function, completely factor the denominator, and then you gather similar factors together. For each linear factor, we write down terms. If it's repeated, we write down different ones. If it's repeated, then there are 3 terms. If it's an irreducible quadratic, we write down like the cx plus d. So what we write down depends on whether or not that factor in the denominator can be factored further or not. And we have to collect like things together, like this example 5. You know, there's, example 6. There's hidden overlapping between these. Like there's an x plus 1 squared in here, and there's an x plus 1 in there. I have to group them together to get that x plus 1 cubed, which then tells me that these 3 things happen. So in order to be successful at the partial fractions, we have to like factor the denominator carefully, and then try to use this guide. There will be some sort of Uber text box in your textbook that tells you every single last possibility given a factorization. But I think what you need to do is just keep working examples until you see it. Yeah.
Can you take up any points where it says are ordered if it's different? If we had A over X squared plus B over
That would be the same answer. Yeah. Yeah, I mean, the ordering here, it could, A and B could be flipped, C and D could be flipped. These are just, it's an intermediate step to going towards an answer. So anyway, so you do the algebra, much like we did today. And what this works out to is 8 plus 6 plus 7x over x squared plus 5 plus 30 over x squared plus 9 over x. Which, of course, what's left there, 8, 6, 7, 5, 3, 0, 9, could easily be integrated, yes? Some people. No? Yeah. Listen, I haven't quite, I mean, morally, how we do this algebra is very much like what we did today, but we need to do more of that tomorrow. So, yeah.
For that one, you would just do partial fractions and for the second term.
This is the partial. The second term is equal to that partial fractions. Multiply.
6 plus 7x over x squared plus 5. Let's see that again.
Oh no, that cannot be further decomposed. X squared plus 5 is irreducible. That's it. That's the end of the road. Yeah.
Oh, I missed it.